first case lying along the c-axis then. Let's try to see how this works. Now let's work on the xy plane. We let c to be 0, so the equation becomes x squared over a squared plus y squared over b squared equal to 0. And for this case, note that this will be 0 only when x and y equal to 0. Right? So when we specify the type of trace, that would be a point. On the xy plane, just only a point. Is that clear? Okay, now the next case on the xy plane. On the xy plane, we let y to be 0, so this equation would be x squared over a squared, and then minus c squared over c squared equal to 0. Okay, let me work out a little bit more here. When we have this, it can be considered as so we can think of x over a squared equal to z over c squared. Or in other words, we can say z over c squared minus x over a squared equal to 0. By square difference, so we have c over c minus x over a, and then times z over c plus x over a. So we're going to have z over c equal to x over a, or z over c equal to minus x over a. And in other words, this one would give z equal to z over ax, or z equal to minus c over ax. So we can say z equal to plus or minus c over ax. And what is this equation? This is the equation of the straight line on the xy plane with slope c over a, right? And this one is the straight line with the slope minus c over a on the xy plane. Both of these passing through the origin. It is like two lines crossing at the origin. Okay, so here we would get z equal to plus or minus c over ax. Okay, and this one is going to be two lines intersect at the origin. On the xy plane, so I don't have space, so just leave it like that. Okay, I will draw the graph of this later then. And when x equal to a, z would be equal to z and minus c. We are going to draw this one later. Now on the yz plane, the equation can be obtained similarly. It becomes y squared over b squared, minus c square over c square equal to 0. We would give almost the same thing. So we would get z equal to plus or minus c over bx, sorry, y. By using the same method here, we would get the same thing, but this is on the YC plane. So these are the straight line on the YC plane. So we would get again the same thing, two lines intersect at the origin on the YC plane. Now it's time to draw this on but now let me do one more. What about on the plane z equal to c? We are going to do some more so that we might get the graph is better. So this will be x squared over a squared plus y squared over b squared. Now if we put c equal to c, then we would get this. And in other words, c squared over c squared would be just 1. So we would get an ellipse on z equal to c. Now I'm going to draw this on the three-main plane. Okay, so this one is simple. On the xy plane, it would be just a point. It would be just a point. Now for on the xc plane, the equation would be z equal to plus or minus c over ax. Now let me draw the y c equal to c over ax when x equal to a. When x equal to a, z equal to c and minus c. So c equal to c. So the first straight line passing to the point AC. This is z equal to c over ax. And another one is passed to the point a minus c. So this is z equal to minus c over ax. These two lines intersect at the origin. So this is the trace on the YC plane. I'm sorry, on the XC plane. And similarly, on the last one on the YC plane, y equal to b. When y equal to b, FC will be c. Is passed to the point BC. This is the point BC, and this is the point B minus C. And so on. Now, on z equal to z, we can get the ellipse. Just keep it like that. Now combine this onto the three-dimensional space. First of all, let me draw on the graph. Okay, first of all, we have got the point 0, 0 there. And on the XZ plane, this is on the XZ plane. This is the point AC. So we're going to have the straight line passing through the origin, crossing together. This is minus A. So this is the point AC, this is the point minus AC, this is the point A minus C, this is the point minus A minus C on the XZ plane. Now on the YZ plane, there are another one. This is on the YZ plane. It would be difficult to draw, but okay, anyway, it is like the line crossing there, and on Z equal to Z, we can have that this is given and another ellipse there. Similarly, on Z equal to minus C, we got the same ellipse there. Okay, when X, this is A, this is B. So we conclude that we can conclude that this is the graph of the elliptic cone. The reason that we call it as elliptic cone because the graph would be like this. Let me draw it better here. Okay, so this is the center of the elliptic cone, and because when we cross section it with C equal to C, this one would be an ellipse. So that is why we call this as elliptic cone. So if we get the graph better here, so this is the one on the this is the line on the XZ plane, and the black one can be this part on the YZ plane. And the blue one here would be an ellipse. This is the point A. This is B. Okay, that's the best graph of cone I can draw now. So this is what we call a cone, or we can say an elliptic cone. Lies along the z-axis, and we can say center at the origin So this is center of the cone, lie along the z-axis here. This is the z-axis. Okay, and similarly, if we want to draw the cone with lie along the y-axis, then this would be a graph of, we can draw this one. This is lie along the y-axis. So this is the cone lies along the y-axis, and its equation would be of the form x square over a square minus y square over b square, and then plus c square over c square equal to 1. And for another one lying along the x-axis, we can also have so this is the cones lies along the x-axis, and the equation would be minus x square over a square plus y square over b square plus z square over c square equal to 1. This is another two cases of the cone. Okay, and similarly to other surfaces, the center of the elliptic cone can move to another point x0, y0, z0. So you can just replace x by x minus x0, y by y minus y0, and z by z minus z0 to get the new center of the cone. Okay, so the information here given in your lecture note there. Okay. Next, let's work on the next examples. Can I take it out? Okay, so let's work on the example on page 27 together. They want you to draw a graph. Just draw a graph. Do not need to find the trace and so on. Just draw the graph. Okay, so this one, the equation would be x squared plus y squared minus c squared and so on. So what we can do, we can just put x together, and y, we only have one y squared there, just leave it like that. And then minus, now put c squared together. This would be plus 6c. If we take minus sign in front of that, then this one can be minus 6c. Because when we multiply minus 1 back, then this would be plus 6c. And the constant minus 8, we move to the right-hand side then. And then we do the square completion of each of these terms so that we can get the new center for the surface. So the first one here, it can be written as 2x can be written as 1x, and then to do square completion, we need to add 1 square to that term. Now for this one, to get 6c, this one should be 3, and then we need to add 3 square there. Now we need to consider this one on the left-hand side, we add 1 square, right? So we add 1 square there. Now with this one, 3 square, even if this is positive plus, but we have the minus sign in front of that. So this is like we subtract t square into the left-hand side, and that is why we need to subtract 3 square to the right-hand side as well. Okay, and now we simplify the left-hand side. This is x squared minus 2, 1x plus 1 square. So it comes out to be x minus 1 square. And for y squared, we can consider as y minus 0. Now for this one, it can be considered as z minus 3. Eight plus 1 become 9. 9 minus 9 become 0. So here the right hand side is 0 now. So this is in the form when a, b, c are equal. You can see this one we can think of like this is over 1 square, this is over 1 square, this is over 1 square. So it comes out to be in the form of x minus x0 over a square, x minus x0 square over a square, plus y minus y0 square over b square, and minus z minus 3 square over b over c square. So a equal to b equal to z. So here a equal to b equal to c equal to 1. When a, b, c are equal, that mean the trace, when we cut it with c equal to 1, we're gonna get the circle. Okay, since the right hand side is 1, this is right hand side is 1, and when we consider left hand side, we would get 2 plus and 1 minus. 2 plus and 1 minus, so this is an ellipse. This is a cone. But when a equal to b equal to c, it would make, it is no longer an ellipse, but it is a circle. So we say that this is a circular cone. A circular cone. Center at the new center become 103. Okay, and lies along what? Since negative sign in front of z, so this is lie along the z-axis. They want you to draw, so no problems. The new center would be the point 103, x equal to 1, y equal to 0, and z equal to 3. So this becomes the point 103 on the XZ plane. And the cone lie along the z-axis, right? When the cone lie along the z-axis, then just roughly drawn, so it may not be that fixed that much. So this is the cone lie along the z-axis and the center at 103. You can see that when we consider z equal to 4, when z equal to 4, just put 4 on that. 4 minus 3 become 1 square. So minus 1 here can be moved to right hand side. then the right hand side would be 1. So this would be an equation of the circle of radius 1. So on y equal to 4, the trace become a circle of radius 1. And so on. Okay, so this is the circular cone. Now, I hope you understand the difference between the equation of elliptic cone and the equation of the ellipsoid hyperboloid. Okay, the right hand side come out to be an important part. If the right hand side is 1, then it can be ellipsoid hyperboloid 1 sheet or 2 sheet. But if the right hand side is 0, and the left hand side come out to be 2 positive, 1 negative, or 2 negative, 1 positive, then it would be an elliptic cone. Okay? Now let's go on to another 2 surfaces. That should be our last 2 surfaces in this chapter because we are done with the cylinder before. So for the next one, it is what we call paraboloid. Okay? So the name of paraboloid came from the word parabola plus OID, which is a suffix of this surface. Okay, so there are 2 types of the paraboloid. We are going to see the equation together. Equation of these 2 surfaces together. Can I take this out? Okay. Now, let's compare these 2 types of paraboloid. Sometimes the paraboloid here, sometimes it's called elliptic paraboloid. Elliptic paraboloid or hyperbolic paraboloid. There are 2 types of paraboloid. So it comes from the word parabola and then plus OID. There are 2 types of paraboloid. One of them is elliptic paraboloid, another one is hyperbolic paraboloid. And as you have seen, the name comes from the word parabola. So that means the trace of this surface should contain the parabola. And you all may have remember that the parabola equation, usually its equation would be in the form of y equal to ax squared or x equal to ky squared, for example. The equation of the parabola usually contain one variable with exponent 1 and another variable with exponent 2. Therefore, one of the key to be a paraboloid, that means the equation of the paraboloid should contain one variable with exponent 1. Remember, all of those quadratic surfaces that we have learned before, it contains x squared, y squared, and z squared, right? But for the case of the last 2 surfaces here, it consists of the word paraboloid. So it has parabola in it. That means some of the variable must be exponent 1. So both of them, you can see, this one, it can be either z to the 1 and x and y to be the square, right? Or even y to exponent 1 and x and z would be the square term. Or even this one, x to the 1, y and z would be the square term. Or even the hyperbolic paraboloid, z to the 1 and x and y come out to be square. Y to the 1, x and z come out to be square, and x to the 1 and y and z would be square. Okay, remember, to be a paraboloid or hyperbolic paraboloid, one variable would have exponent 1, another 2 variable would have exponent 2. And that would be the characteristic of the paraboloid. Okay, now once we have that, there are many forms, okay? And what you have to keep in mind is, to be a paraboloid, the exponent, the variable with exponent 1, that means the paraboloid would lie along the z-axis. The exponent 1 can tell us it would be the paraboloid lie along the y-axis. So it would lie along the axis of variable exponent 1, say. Okay? And similarly to hyperbolic paraboloid, we can say the same thing. With c to the exponent 1, this is lie along the z-axis. With y to the exponent 1, we can call it as lie along the y-axis. And lastly, x to the exponent 1, this can be called as lie along the x-axis. Now, what we have to do to write down the equation of the paraboloid, we need to write down the variable of exponent 1 on the left-hand side, and then push everything to the right-hand side. Another 2 square should be on the right-hand side. Okay? Now, once we just move them to the right-hand side, the left-hand side contains only one variable with exponent 1. And then the way we can find out whether what the surface is, just look at the side. If these two square terms have the same sign, either both positive if it both positive, or it can be both negative. If the sign of these two square terms come out to be the same, then it would be elliptic paraboloid. Okay? And the sign here, this lie along the z-axis, right? If both of them are positive, then it would be open on positive z. Open on positive z. Because if these two are positive, then z is positive, so it would be on positive z, because z would be positive. But however, if both of them are negative, then this one would be negative. It would make z to be negative. So it would open on negative z. Okay, similarly, this is open on positive y. This is open on negative y. This is open on positive x, and this is open on negative x. I will explain you later what does this mean. But however, the equation of hyperbolic paraboloid, the right-hand side contains both x squared and y squared, but to be hyperbolic paraboloid, hyperbola, right? Hyperbola equation should have one positive and one negative. Okay, and that is why the case of hyperbolic paraboloid here, we're gonna have the sign of these two terms come out to be different, namely one positive and one negative. One positive and one negative. Or it can be positive at x, positive at x and negative at y. So this would be hyperbolic paraboloid lie along the z-axis. But there is no open on what? Okay, so similarly, we have got one negative, one positive. Or one positive, one negative. Understand? So the difference between elliptic paraboloid and the hyperbolic paraboloid, it would be just the sign of this square term. If the sign in front of this square term are the same, it would be elliptic paraboloid. If the sign of these two squares come out to be different, then it would be hyperbolic paraboloid. Okay, so I hope you understand the equation of these two surfaces. Now, it's time to draw the graph of the paraboloid. So let me begin with the paraboloid here. So this is an example of the paraboloid lie along. This is the first case. It would be a paraboloid lies along the z-axis because z has exponent 1. And since the signs are both positive, so this one is open on positive z. So the graph come out to be this. So here positive z. The shape of the graph would be like that, like this. Okay, the cross section here is an ellipse. And that is why sometimes it is called elliptic paraboloid. Okay, so you can see that the cross section of this would be our parabola, and cross section here on the xy plane, it would be another parabola. Okay, so this surface combined by two parabola, then the shape of the elliptic paraboloid would be given like this. And the bottom here is called the center. Okay, so this picture has center 0, 0, 0. Center 0, 0, 0. And similarly, the paraboloid, they can move their center into the x0, y0, z0. What we can do is we just replace x by x minus x0, y by y minus y0, and z by z minus z0. And that is the way we can move the center of the paraboloid. Now let's try to draw this graph. You will see why we get the graph like what is given there. So to draw the graph of this, now let me add one more on z equal to 1. This is the trace equation. On the xy plane, we let c to be 0. So the equation come out to be 0 equal to x squared over 4 plus y squared over 9. That one, the right hand side is greater than or equal to 0. The left hand side is 0. So this one would be xy equal to 0, 0. It's just a point. 0, 0 on the xy plane. Now on the xz plane, we just let y to be 0. So what we get would be z equal to x squared over 4. Or in other words, we can say this is plus 1 over 4 x squared. Z equal to plus 1 over 4 x squared. This one would be a parabola. And the coefficient of x squared is positive, so z would be always positive. So this time we can say open on positive z. And lastly, we let x to be 0, so this one we would get z equal to y squared over 9, or we can say 1 over 9 y squared. And this is another parabola. Open on positive z again. Now lastly, if z equal to 1, let z equal to 1, we would get 1 equal to x squared over 4 plus y squared over 9. And that equation would be nothing but x squared over 4 plus y squared over 9 equal to 1. And that would give an ellipse on z equal to 1. On the xy plane, on the xz plane, on the yz plane. On the xy plane, it would be just a point. On the xz plane, when x equal to 0, z equal to 0, when x equal to 1, it would be 1/4. When x equal to 2, then it would be 1. So it passes through the point 2, 1. And minus 2, 1. So the parabola would pass through these 2 points. This is z equal to 1 over 4x squared. Now, another one on the yz plane, we have this, then when y equal to 3, then z equal to 1, so it passes to the point 3, 1. So this is the point 3, 1, this is the point minus 3, 1. And this equation would be z equal to 1 over 9 y squared. It would be the parabola on the yz plane. And on z equal to 1, you can get another ellipse when x equal to 2, y equal to 3. And we draw another one on the xy plane. Okay, so we have two parabola there. And on the plane z equal to 1, that would have the ellipse when x equal to, when the distance is 2, and this is 23. So this is 2 units, and this is 3 units. So we have got another ellipse. Or we can even get the larger ellipse there. When z is larger and larger, then we would get the larger ellipse there. And that is why the shape of this surface become like this. Okay? Or in other words, if we draw it on that, on the xy plane, so this is the one on the xc plane. And this is the one on the yc plane. And the ellipse on the plane c equal to 1 would be right there. Okay, so that would be the graph of the elliptic paraboloid. When you cross section this, we would get an ellipse. So we call it as elliptic paraboloid. Okay, this is the way to draw the graph. Okay, and this is the paraboloid, elliptic paraboloid, lie along elliptic paraboloid. Or elliptic paraboloid or just paraboloid. Paraboloid lies along the z-axis. Here's the z-axis, okay, and open on positive z. Okay, that is the elliptic paraboloid lie along the open on positive z. Now let me draw another 5 cases. Another 5 cases. Let me take it out then. Now there are another 5 cases, right? So if we have this can be z equal to minus x squared over a squared minus y squared over b squared. Okay, this is lie along the z-axis and open on negative z. We can have this. This would be y equal to x squared over a squared plus z squared over z squared. This is open or positive y. So it would be the paraboloid lie along the y-axis and open on positive y. And you can guess another 3 cases. This is open on negative y along y-axis, open on negative y. So its equation should be y equal to minus x squared over a squared minus z squared over c squared. And another 2 cases with lying along the x-axis. One of them would be this. This is positive x. So it would lie along the x-axis and open on positive x. Okay, and the equation of this case should be, well, this is negative y, this is positive x. No, I'm sorry, this is x, this is y. And another one would be, okay, this one would be x equal to y square over b square plus c square over c square. And for this one, it would be lie along the x-axis, but open on negative x. X would be minus y square over b square minus c square over c square. Okay, so I hope you understand what that is mean by open on negative c. So open on negative c, that means this part is negative c. Open on positive y, open on negative y, open on positive x, open on negative x. Okay, and the equation can be done by, if it's negative c, then the sign would be negative. Now let me end up this chapter by the last case. Okay, we are going to move on to the case of hyperbolic paraboloid. Okay, so the hyperbolic paraboloid can be considered as the most difficult surface to draw. Okay, the most difficult surface to draw. This is the pictures of the quadratic surfaces, the hyperbolic paraboloid. This is lie along the z-axis because c has exponent 1. Minus x squared over a squared plus y squared over b squared. So the shape of the graph would be like this. If you look at the shape of the graph of hyperbolic paraboloid, you see that the shape of the graph are quite similar to the body of a horse. So you can think of this part as a neck, the head of the horse, and this one would be the tails. Okay, and the z-axis can be considered as a man who riding a horse. Okay, so this is the man head, and there is riding the horse over there, so his two legs would be over there. So that is why the origin here is what we call the center of the hyperbolic paraboloid. So in some sense, the center of hyperbolic paraboloid, the case of hyperbolic paraboloid, its center is sometimes called a saddle point. It is just the point that the man is riding a horse there. So the center is sometimes called the saddle point, because it is like similar to the horse saddle there. Okay? And okay, so let's see. Okay, and I have told you before the equation would be one variable with exponent 1, another two variable with exponent 2, and the sign of these two squares come out to be different. That is the equation of hyperbolic paraboloid. Now, note that the center of the hyperbolic paraboloid, or the saddle point here, can be changed to the point x0, y0, c0 in the same way. Replace x by x minus x0, y by y minus y0, and z by z minus z0 to move the center of the hyperbolic paraboloid to the point x0, y0, z0. Now, let's try to draw how to get the graph of this hyperbolic paraboloid as this. So let me just draw the shape of the graph like this. So let me change the problem a little bit, because if in this direction it would be difficult to draw. So let me change this a little bit by, instead of positive x and negative y, let's change this to negative x squared over 4 and then plus y squared over 9 instead. It would be easier to draw. Okay? Just change the problem a little bit. Note that this one would be very complicated to draw, okay? So let's begin with the trace with the three main plane. So for the trace equation on the xy plane, we let z to be 0. Right? So that would give 0 equal to minus x squared over 4 plus y squared over 9. So if we solve for this, we're going to have y squared over 9 equal to x squared over 4. So we're going to have, you can try to do by yourself, that one become the plus or minus y equal to plus or minus 3 over 2x. That become two lines intersect at origin. Say on the xy plane. Now on the xz plane, we let y to be 0. We would get z equal to minus x squared over 4. That one would be a parabola open on negative z. And on the yz plane, let x to be 0. When x equal to 0, we would get z equal to y squared over 9. And that would be another parabola. You can see that the trace contains two parabola, and that is why it has a name, paraboloid. And you see later that it has got the name, okay, this is a paraboloid open on positive z. But actually, to draw the graph of this better, we may need another 2. So let's say z equal to 1. And I will do z equal to minus 1 as well. We have to need a lot of traces to get this complicated surface. On z equal to 1, we would get 1 equal to minus x squared over 4 plus y squared over 9. And this equation come out to be a hyperbola. And the name hyperbolic paraboloid come from this hyperbola. Okay, and note that positive is on y, right? So the vertices on y-axis. And for at c equal to -1, we would get -1 equal to -x squared over 4 plus y squared over 9. We multiply by -1, so we get x squared over 4 minus y squared over 9 equal to 1. I'm so sorry, my green color is run out. So this is also a hyperbola. But this one, vertices would be on the positive x. Now we are going to draw these 5 traces. On the xy plane, it becomes 2 lines pass through the point x equal to 2, y equal to 3. This is on the xy plane. This is on the xc plane, and this is on the yc plane. On the xc plane and on the yc plane. When we draw on the xc plane, when x equal to 2, y equal to -1, so on the xc plane, we have passed through the point 2, -1, and -2, -1. So the parabola would be in this shape, open or negative z. Okay. Now, the black one on yz plane, y equal to 3, then z equal to 1. So it passes to the point 3, 1 and -3, 1. And that would be the parabola open on positive z. Okay, and then next one we are going to do another 2. Say on z equal to 1. On z equal to 1, it would be the hyperbola under x is 2. under y is 3. And this time, the vertex is on the y-axis, so the hyperbola would be at y equal to 3 and minus 3. Whereas another one on z equal to minus 1. This one under x is 2, under y is 3. So we have got this. But this time x is positive, so the hyperbola would have axis on the x-axis. So it would be different shape there on z equal to 1 and z equal to minus 1. Oh, I'm sorry, I should use the green color for this one. So that you will see the difference in the when we combine together. Now it's time to combine. Okay, try to look at this carefully. It is complicated. Let me do this one first, 3, 1. Okay. And on the xz plane, x equal to 2, 1, 2. This is at minus 1. Now, let me keep this one at the last. So the next one on the x on z equal to 1. On z equal to 1. You can see that the vertex is on the y-axis. So if we have drawn the x, if we have drawn the x-axis and the y-axis there, this is when the distance is 3 and this distance is 2. Then the hyperbola here, it would be on this axis. So we're going to have the hyperbola here because it would be on the y-axis. So this is like the y-axis, right? So we can have the hyperbola like this on z equal to 1. On z equal to 1, we're going to have the hyperbola like this. Or even when the larger z, we would get the hyperbola there. Okay? Now, what about on z equal to minus 1 here? You can see that on z equal to minus 1. Here, this is on the x-axis, this is y. This is x, this is y, right? And the vertex is on x equal to 2. And this is the point x equal to 2. And this is x equal to minus 2. So the hyperbola that you would get, it would have the vertex here, there. And on that, it would be another one here. And even when we have a lower values, then we would get another hyperbola like this as a level. And for another part as well. Okay? Once we have this, you can see that the hyperbola here and the green hyperbola would be in another direction. So we can combine this together. The graph of the surface come out to be like this. So the hyperbola here should be like that. It is difficult to draw, as I have told you before. This is the best surface I can draw. For better understanding, let's try to look at, okay, the pictures on this. Okay, I can explain you a little bit better. Can compare with this one. Here, on the YC plane, the black one is this one. Okay. The red one would be this. And the blue one. This is the blue hyperbola that I have tried. This is on z equal to 1. And for a larger z, it will be a hyperbola there. Now for the green one at the bottom, it comes out to be this. This is z equal to -1. We have this hyperbola. And another one. You understand? Okay, and that is the graph of the hyperbolic paraboloid. And once we have many traces, then we can form a surface like this. Okay, so that is how it works. So you can see that the level surface when z positive, it would be the hyperbola, the blue one. But when we consider the level curve when z equal to negative value, it would have the shape like the green one there. That is the hyperbolic paraboloid lie along the z-axis. Okay, so you can think of like lie along the z-axis here. You can think of like this. We have a man sitting on a horse, and the body of the man here would be the z-axis, which is the axis that it lie along to. And if we change this to be minus, if we multiply both sides by minus, then we can guess. So if we have minus c equal to, no, actually, I just want to, what about if we just put this one to be positive x and negative y? In that case, we can just flip this surface into another direction. So the graph would be, the shape of the graph would be like, it would be like this instead. So this is negative z, this is positive z. When we switch, when we put this to be minus, Is that correct? Right, we're gonna have this thing, yeah. Because on the YZ plane, this one would be negative, right? We're gonna have this surface instead. And for another four type of this quadratic surface, you can just flip this surface in the direction. Okay, it would be difficult to draw. I can only draw it in this direction. Okay, so to have the graphical calculator might help you understand all another four surfaces better. Okay, because I just have shown you how to draw it then. Okay, and that would be all. And here at the end, there would be a picture of the graph that is plotting by the graphical calculator. Okay, so you can see that the center would be over there. It is difficult to draw, so. Okay, that would be all for chapter 3 then. Okay. Now we have 10 minutes, so let me begin chapter 4. Let me begin chapter 4 for a little bit. So in chapter 3, mostly we have learned the concept of function of more than one variable. The function can have more than one independent variables. Like the function of two variables, you have that, the graph would be all surfaces. Okay, you are going to use the way to draw the graph of the surface again in the next semester, which is the double integral and so on. So we're gonna move on to another topic, which will be related to the derivative of the function of more than one variable. Okay, so the next chapter, chapter 4, it would be about the derivative of two variable function. When we have the derivative of two variable function, how can we consider that? So think of what that is mean by derivative of one variable function. If you all can remember, when we have a function of one variable, the only independent variable would be x. And what is the meaning of derivative? The meaning of derivative, it comes off the concept of the ratio. We are comparing the ratio, namely we compare the chain of the function compared to the chain of independent variable, and we just take the limit. Let the chain of independent variable here to be very small. Okay, that come out to be derivative, or it would be the rate of change at the instantaneous time. Remember. Okay, so this is the concept of the rate of change. We are finding the rate of the function change compared to the change of x when x has changed very small. Okay, so by the idea, we just let the point x, we just let x has changed to be x plus delta x. Right? Just let x to change a little bit, and the numerator here would be the change of f. F at the end minus f at the beginning. This would be the chain of f. So the derivative would be the chain of the function over the chain of the independent variable x, and take the limit to be chain of x very small, and that is the derivative of the function at the point x. Right? But now, if we have the case of the function of two independent variables, this definition does not work because we have two independent variables. Since there are two independent variables. Now, if you want to find the derivative, you need to specify, you want to know the rate of the function change compared to the change of which variable. You might want to know the effect of the change of x, effect to the change of the function, In that case, if you want to see how much the chain of x affect to the chain of the function, in that case, you should keep y to stay the same. If you want to see the effect of x, we need to keep y to stay the same and let x change only. Okay? If in that case, if you want to find the derivative with respect to the chain of x, we need to keep y to stay the same. In that case, if we want to find derivative with respect to x, then you need to let the point x, y, just let x to be changed by delta x unit and y to stay the same. So the derivative with respect to x, we just let x change, right? We just let x change and y to stay the same. That means the change of the function, it would be this. And that one would be fxy. Just let x change and y stay the same. And then divided by the change of x. And when we take the limit delta x go to 0. That would be the derivative with respect to x. Derivative with respect to x. We want to see how much, if x change a little bit, how much the function would affect. Namely, if the function is increasing or decreasing when x is changed a little bit, and y does not change. That is what we call the derivative with respect to x. Similarly, if we want to find derivative with respect to y, that means we want to know if y is changed a little bit, then how much the function would affect, the change of the function would affect. In that case, we need to let x to stay the same and let the value of y to be changed a little bit. That means we're going to let y to be changed by delta y unit. So by definition, the end point would be x of y plus delta y and minus f at the beginning, and the change would be delta y, and we just let this change to be small. That would be the concept of derivative with respect to y. So for the case of function of more than one variable, if you want to find the derivative, you need to specify which independent variable we are considering. We just want to see the effect of change of x to the function, or we want to see the effect of change of y to the function. Okay? So in other words, for the case of two variable functions, there are two types of derivative. Okay, there are two types of derivative. The derivative with respect to each independent variable, it is defined differently. Okay? To find derivative fxy, we need to calculate derivative with respect to each independent variable separately. Okay? And the derivative with respect to each independent variable here, it is what we call partial derivative. Okay? This is derivative with the x part, so we call partial derivative with respect to x. Or we find derivative with the part of y, then it is what we call partial derivative with respect to y. Okay, that is the idea. If there are more than one independent variable, to find derivative, you need to specify which independent variable we are considering. For the case of three variable function, there are three types of derivative and so on. Okay? And if you understand the concept here, that if you want to see how much the effect of change of x, then you need to let other variable to stay the same. That means we might need to consider y to stay the same as a constant. So the way to calculate the partial derivative is in this way. To find the partial derivative of fxy with respect to one variable, we just let that variable change only. Another input variable should not change with no confusion. So we need to let another input variable to be constant. For example, to find partial derivative with respect to x, we consider y as a constant. Do not let y change, just let x change only. And similarly, if we take derivative, and once we let y to be constant, when we fix y to be constant, then the only variable would be x. So this is considered as a function of one variable of x. And then we can do the ordinary derivative of one variable function with respect to x. We can do d by dx with that one. When y is fixed, you can think of y fixed at y0 and so on. If this is a constant, then we just take the derivative of this with respect to x as the case of one variable function. Similarly, if you want to find derivative with respect to y, you need to let x to be constant and take d by dy for that as the derivative of one variable function. Okay, and that is the concept of partial derivative. Okay, so for next time, I'm going to talk about the new notation for partial derivative and the example how to calculate the partial derivative of a given function. Okay, because the time is up now. So, and one more thing, we have no class on Friday because it is a Thailand holiday. So, but what I'm thinking is for the makeup class, it might be difficult to have the makeup class. So I might record a video. So, and we assign you to just watch the video as the makeup class then. What I'm thinking in my mind is I'm going to record the video of chapter 5, which is the next chapter. The chapter 5 would be about the application of partial derivative. That means you can watch that video once we finish up chapter 4. Once you have learned all concepts of partial derivative, then the chapter 5 about application of partial derivative, you may need to watch on the video only. I would not cover chapter 5 in class, okay? Because it is assigned as a makeup class. You may need to find your free time to watch the video of chapter 5 by yourself. I may need to find some time to record that video, okay? But once we finish chapter 4, I will skip chapter 5, and then I will begin chapter 6 instead. And chapter 6 would be all about integration. We don't need chapter 5 for that, so, okay? But do remember that the topic of chapter 5 might be in the quiz or even in the final exam. You really need to go on watching that video of the makeup class by yourself, okay? Okay, for next week, I'm going to continue chapter 4. Once I finish chapter 4, I will cover chapter 6 in class. Chapter 5 would be the self-watching video by yourself. Okay, understand the whole chapter. It is not that big chapter, so okay, maybe we may need about like 2 or 3 hours to finish up that. Okay, I will record the